Hello, everybody. I'm Felix Neutatz, and today I'm excited to share our work on declarative feature selection. And this is joint work with Felix Biesmann and Siavash Abedian. Nowadays, ML applications are not only about model accuracy anymore. There are many more dimensions. There's fairness, deployability, explainability, privacy, safety, and many more. Some of these dimensions have been addressed individually in literature by either adjusting the model objective or the model architecture. However, this approach requires heavy ML expertise. Therefore, we were asking ourselves, can we also enforce these constraints in the data? More specifically, we looked into feature selection. So here we plotted the original feature set of the Compass dataset. The Compass dataset contains offenders and whether they will relapse before trial or not. And the original feature set is here plotted against the following dimensions. First, empirical robustness against adversarial examples and F1 score. And on the other hand, equal opportunity, which is a fairness score, and the F1 score. And now if we apply feature selection, we can in fact see that by adding and removing features, we can both yield a higher robustness and a higher fairness. So we showed here that indeed, we can leverage feature selection to address a large number of ML application constraints. It would be great if you could formulate this problem in a declarative fashion. So the user would specify the constraints, for example, fairness and adversarial robustness, and our system would find the features that satisfies these constraints. And the great thing about this formulation is that we do not require ML expertise, and we can satisfy multiple diverse constraints simultaneously. But now the question is, which feature selection strategy do we actually choose to achieve this goal? And the challenge is that there are actually a lot of feature selection strategy, as you can see here in the taxonomy. So it's a big challenge to choose the right one out of these many strategies. To this end, we make the following contributions. We analyze which strategies are suitable in which cases for diverse novel ML application constraints. And we propose a DFS optimizer that can choose the right feature selection strategy that is most likely to satisfy a given scenario. This DFS optimizer has to identify a feature selection strategy that can actually satisfy the given ML scenario. And in order to make this decision, it has to consider the following components: the data set, the ML model, and the constraints. The DFS optimizer also has to follow some requirements. First, no trial and error is allowed, so we do not want to execute multiple feature selection strategies sequentially, just to find one that actually works. Secondly, we require extensibility to more constraints and strategies, and related to this requirement, we do not want human supervision. So every time a new constraint is added, the human should not need to label or add any rules. And to implement a DFS optimizer that can successfully map an ML scenario to a feature selection strategy and follow all the requirements, we propose self-supervised meta-learning. And for the details, I would point you to the paper or to the long talk. To evaluate our DFS optimizer, we designed a benchmark of more than 3,000 scenarios based on 19 datasets, 6 ML application constraints, 3 classification models, and 16 feature selection strategies. And here are the results of the benchmarks. So first, we see that none of the strategies is always the fastest. And secondly, we see that none of the strategies can satisfy all the scenarios. Further, we see that indeed our DFS optimizer can achieve 10% higher coverage than the single best strategy. However, this is still a large gap to the theoretic optimum, so there's still a large potential for future research. To conclude, we propose declarative feature selection, which is a new framework to enforce multiple diverse ML application constraints using feature selection. And for this framework, we propose an optimizer that leverages self-supervised meta-learning. And you can find the code openly available on GitHub. And with that, I'd like to thank you. Goodbye.